Now we're going to continue our discussion about gas laws. We're going to talk about how an ideal gas can be used to explain the gas laws, and we're going to just consider how the ideal gas equation comes about, and then we're going to try some examples of how to use it. Okay, so the first law we're going to look at is Charles' law, named after the physicist Charles, who did some experiment in this. And so basically what we're going to do is, here's the apparatus. So this is the experiment that was designed. So apparatus, now we have a thermometer in here, and now what this is for is to measure, we're going to measure the temperature. Okay. And now what we have is essentially an apparatus like this. Okay, so there's some gas in here, just like that, and in here, this is filled with mercury. Okay, now the gas is surrounded by water, so this right here, this is water, so it's surrounded by water, and we heat it from below. Okay, so what we're doing essentially is looking at how quickly the temperature changes. Okay, so we have some heat from below, we're changing the temperature, that's our independent variable, and what we are doing is keeping the pressure constant. Now if we move along here, this height, okay, always remains constant. Okay, and the reason for that is the total pressure within this system is just 1 atmosphere, so the atmospheric pressure, plus pressure can be given by this equation, rho GH, where rho is the density of the material, G is the gravitational constant, and H is the height. Okay, so if we keep adjusting the amount of mercury in the tube so that H remains the same, that means that the pressure is constant. So P, pressure, remains constant in this experiment. Okay, and what we are doing is measuring the volume of gas in here as the temperature changes. And we find, if we were to plot this, so temperature is the thing we are changing, independent variable. We're measuring the volume, the dependent variable. And what we find is a relationship, something like this. So as the temperature increases, the volume will also increase at a constant pressure. Okay? Now, this is interesting because if we extrapolate this backwards, we arrive at a point here where the temperature is 0. And that is just absolute 0 on the Kelvin scale. 0 Kelvin. Okay? And you find this with any gas that you use. You're going to find a relationship like this. It always extrapolates back to a point where at 0 volume, there is 0 temperature. Okay? Now the relationship we find for this is that V, since volume increases as temperature increases, V is proportional to T, which we can also write as V over T is a constant. Alright, and if we have two different substances, let's say we have one situation where we have a volume V1 in here, so V1 at a temperature T1, if we then change that temperature to a temperature T2, the volume will change correspondingly to V2, where these ratios are exactly the same, okay, which is the outcome when this is proportional. Okay, so that is Charles' law. The next law we're going to look at is the Boyle-Mariotte law. Now in this experiment, what we have is basically we have a piston. Okay, so let's just add this here. Okay, so this is a piston, and we have some gas in here. Okay, so we have some gas, and what we are essentially doing is having a constant temperature. Okay, so to have that constant temperature, we basically have thermally insulating material so that the temperature remains constant. To keep the temperature constant, we could heat it as well to make sure that it remains constant. So if there's any cooling or any, or we could cool it actually. Okay, so whatever the temperature is going to be, I'm skipping ahead here. Whatever the temperature is, we could basically heat it or cool it to keep it at that temperature. But the important point to remember here is that the temperature is constant. Okay, and what we are going to do is increase the pressure. Okay, so to increase the pressure in this, we vary weights on the piston. So what we can add a variety of weights onto the piston. That will cause the piston to go down, okay, which decreases the volume of this cylinder, and therefore we can measure with let's say a pressure gauge, we can measure the change in pressure as that volume changes at a fixed amount. Okay? And what we find from this relationship, from this experiment, is that so we vary the volume and we're measuring the pressure change, and what we find is a relationship that looks something like this. Alright? So it's a curve. Now, what we get from this is that the product, so P is proportional to 1 over V. So as the inverse of the volume changes, pressure will also increase. Another way of saying that is PV is constant. Okay, so the product of PV will always be a constant term. So if we have we put some weight on with a specific volume that corresponds to a certain temperature P, or a certain pressure P1. If we then change the volume to something like V2, pressure will be P2. Now the product of these two will be the same. Okay, which is where this relationship comes from. Okay, so we have another relationship here. Before we had a relationship between volume and temperature, now we've related volume and pressure. So the only thing that remains to do is look at pressure and temperature. Now in this experiment, what we essentially have is, again, we're dealing with gases here. And so what we have is some gas that is immersed in water. Okay? So this cylinder has a set volume that is unchanging. We immerse this volume in water. Okay, so we can change that temperature. So this is immersed in water, and then we heat it up from below. So we want to add heat. This is some gas. Okay, so the volume remains constant. And this experiment, we heat up, so we increase the temperature, and we want to find out what happens to the pressure. We measure pressure using this pressure gauge. What we find from this experiment is, as the temperature increases, the pressure will also increase linearly, which is very similar to the volume temperature relationship. And once again, if we extrapolate this backwards, we find that there is, as pressure goes to 0, temperature also goes to 0. On the Kelvin scale, this is 0 Kelvin. Okay, so with this proportionality, we find that P is proportional to T, therefore P over T is a constant. Okay, so this is a constant, therefore, if we were to go P1 over T1, so we have some temperature, a pressure that corresponds with that temperature. Now if we increase the temperature to T2, the pressure will also increase to P2, and the product of these two numbers, or sorry, this ratio between these two numbers is exactly the same. So now we have our three laws. We have V over T equals K, so I'm going to make K my constant term. We have PV equals K, and we have P over T equals K. So we have these three terms. If we combine these three, what we get is PV over T is a constant. Okay. Now, if we change the amount of gas, so let's say we've used the same amount of gas in all of those experiments. Now let's say we want to see if this is universal and we change the amount of gas. So we do 3 or 4 different experiments, each with different amounts of initial gas. What we find is that the relationship doesn't change whatsoever. However, we get this term, n time constant. Okay, so this relationship, this number, whatever it is proportional to the number of moles of gas. Okay, so this relationship still holds, it's just that it will be a bigger number, and that is proportional to how much gas there is, so how many particles of gas there are. All right, and now if we repeat this experiment a number of times with different moles of gas, what we find is that this constant remains exactly the same. So no matter how much gas we use, no matter what gas we use, this is a constant term. And that constant term is something that's called the gas constant. So let's go around here. That is the gas constant R, which has a value of 8.31. We can figure out the units just based on the fact that this is moles, and these units right here, pascals, meters cubed, and temperature. And what we find is that this has units of joules, Kelvin to the -1, moles to the -1. Knowing that that is the number R, we can finalize the equation as PV over T equals NR, or writing in the more common form, PV equals NRT. Okay, so that is some motivation behind where the ideal gas equation comes from. Next, we're going to look at some examples of how to use the ideal gas equation.